that no dangerous combination of chemicals occurs together in the same warehouse. So, this is the problem. And so, here in the first column you have various chemicals, all the 13 chemicals listed, and for each chemical you have a list of other chemicals which are dangerous when stored together with the first chemical. Okay? So, the chemicals in the row are the dangerous combinations when stored with the chemical in the first column. Okay? So, this is the code, and so so the question is what is the how to solve this problem, and we will see that although in the statement of the problem there is no apparently on the surface there is no graph, very soon the neatest way to solve this problem is introducing a graph, and then we will be naturally led to questions of vertex coloring of that graph. So, construct a graph as follows. The vertices of the graph are the 13 chemicals C1, C2 up to C13, and edge joins C1, Ci and Cj if they appear in the same row. Okay? So, in this table. So, in other words, Ci is connected to all those Cj such that Ci and Cj are not safe to store in the same warehouse. Okay? And now, the warehouses will be represented by the colors. So, if I put a certain color on a certain vertex, remember the vertices are representing chemicals. So, if I put a certain color on a certain vertex, it means that I put that chemical corresponding to that vertex in that warehouse corresponding to that color. Okay? So, this is the sort of the encoding, and so under this encoding, so we have encoded the problem in terms of a graph. Let us now understand what it means to have a safe allocation of chemicals to warehouses. So, a safe allocation to chemicals to warehouses is an allocation of chemicals to different warehouses, so that no two dangerous chemicals occur in the same warehouse. Now, our code was that vertices represent chemicals and warehouses are represented by colors. So, this means that no two vertices which are dangerous in combination, which means that they are connected, no two vertices which exactly translate into no two vertices that are connected by an edge, can be put in the same warehouse, so they can have the same color. So, exactly the assignment of these chemicals in a safe manner to warehouses leads to a vertex coloring of this graph, which is proper. Proper because in a proper vertex coloring, no two vertices which are connected by an edge can have the same color. Here in this example, two vertices are two chemicals. They are connected by an edge if and only if they are dangerous in combination together. So, proper vertex coloring means two different colors for these two vertices, which means that they are not in the same warehouse. They are allocated to warehouses of two different warehouses which represent two different colors. So, the minimum number of warehouses is therefore the minimum number. So, the number of warehouses is the number of colors in order to do this proper vertex coloring, and the minimum number of warehouses so that you can store these chemicals satisfying these constraints is therefore the minimum number of colors you need to do a proper vertex coloring of this graph. So, in other words, the minimum number of warehouses needed is just the chromatic number of the graph. Okay? So, if you take the table in the previous slide and draw the edges for all the dangerous combinations of chemicals, the graph will look like this. So, this graph contains a triangle. So, at least three colors will be needed, because we know that if a graph contains if a graph contains a particular subgraph, then the chromatic number of the original graph will be at least as large as the chromatic number of the subgraph, right? Because a proper vertex coloring of the original graph, if you restrict to the subgraph, is also a proper vertex coloring of the subgraph. And if you have a triangle, then the chromatic number is of course 3, because you need 3 colors, 3 different colors to color the vertices of a triangle in a proper way. So, at least 3 colors are needed, and actually 3 colors are sufficient, because you can obtain a coloring like this, and this you can actually, it's not that hard to come up with this coloring by hand, because this graph you can look at it as a combination of many triangles, and then they are joined in the center in some manner. So, basically you just color these triangles in a slightly careful way, and then it works out to give you a proper vertex coloring with 3 colors. So, so since there is a proper vertex coloring with 3 colors, the chromatic number is at most 3, and we have already seen that the chromatic number has to be at least 3, because it contains a triangle. The original graph contains a triangle. So, the chromatic number, therefore, in order to satisfy both the constraints, both the inequalities of being at most 3 and at least 3, it has to be exactly 3, right? That's the only. So, the number of warehouses, minimum number of warehouses the factory needs in order to store its chemicals safely is 3. Okay? Any questions? Okay. So, let us now move on to the domain of coding theory. So, in coding theory, we will first study modular arithmetic. So, what is modular arithmetic? It is an arithmetic dealing with periodic computations, and it was introduced by Gauss, the famous mathematician, after whom the name Gaussian is named, and essentially he made fundamental contributions to a lot of fields of mathematics, and including the normal distribution. At least its importance was emphasized by Gauss. So, his contributions are so fundamental. And modular arithmetic, I mean, although the name modular is there, is actually very similar to ordinary arithmetic. So, let us see what it is. So, the modular arithmetic revolves around the concept of congruence. So, usual arithmetic revolves around the concept of equality, right. So, it is very important to understand when 2 numbers are equal. Similarly, in modular arithmetic, equality is replaced by congruence. So, what is congruence? Suppose a and b are integers such that the difference is a multiple of a positive integer n. So, in other words, a minus b is divisible by n. So, then we declare that a is congruent to b modulo n. Okay? This is often abbreviated by saying that a is congruent to b mod n. So, the above equation is called a congruence equation, or simply congruence, and the integer n is called the modulus. Okay? Any questions? So, let us see some examples. So, suppose you are using the 24-hour clock, and a is congruent to b mod 24, then a and b must be the same time, but maybe on different days. So, you do not care about which day of the week it is, you are just interested in whether it is the same time, and then you just take the time mod 24. So, the second example is even more pertinent. So, suppose you are using a 12-hour clock. So, like the old fashioned wristwatches, like the one I am using. So, if you are using an old fashioned wristwatch, then 12-hour clock means that a is congruent to b mod 12. So, a and b are the same time, but they may be on different halves of the same day or different halves of different days. So, essentially what this is saying is that you are a is congruent to b mod 12 means that it is the same time up to am or pm. Okay? So, it is 7 o'clock and you do not care about whether it is am or pm. So, the question is that, so the point is that suppose you are just focused on a single day. So, there could be 7 am or 7 pm. Now, if you do not care about that and you want to do your arithmetic without caring about that, then you just say 7 o'clock. Okay? And then of course, there are certain rules how you want to manipulate, how you can manipulate time under that situation, because if you add 7 hours and 6 hours, then it will become more than 12 hours, so you have to adjust according to the 12-hour clock, etc. So this collection of rules when you operate in this kind of restricted scenarios is called is essentially the content or the core of modular arithmetic. And numbers which are not integers, for example fractions, are not permitted. Okay, so we will just be dealing with integers. So properties of congruences. So here are some basic properties of congruences. If the remainder of A when divided by n is r, then A is congruent to R mod n. Okay, so this is very simple because if A when divided by n is r, so let Q be the quotient, then A is equal to Qn plus R, right? So then if you take A minus R, this is Q times n, so n divides A minus R, so A is congruent to R mod n. The remainder of 322 when divided by 3 is 1, this is easy check, so 322 is congruent to 1 mod 3. Okay. So here are some further properties of congruences. So A is congruent to B mod n if and only if they have the same remainder when divisible by n. So here, so in the slide we have discussed a proof, but let us write down a quick argument to see why this is the case. So if A, so you can, if you divide A by n, let Q1 be the quotient and R1 be the remainder. Similarly, if you divide B by n, let Q2 be the quotient and R2 be the remainder, then A minus B is Q1 minus Q2 n plus R1 minus R2. Okay. So of course, so therefore, if you divide A minus B by n, then you will get R1 minus R2 as the remainder, and this R1 minus R2 you can check that in absolute value it lies between 0 and n, there 0 and n minus 1, therefore A minus B is divisible by n only if and only if this is divisible by n, and since in absolute value it lies between 0 and n minus 1, therefore it is divisible by n only if this is 0, and if this is 0 then R1 has to be equal to R2. So basically this is the rough argument as to why A minus B, A is congruent to B mod n if and only if A and B have the same remainder when divided by n. Okay, because essentially that's A is congruent to B mod n if and only if R1 is congruent to R2 mod 2, when R1 and R2 are the remainders when A and B are divided by n. So any questions? Okay, so let's now move on to further properties of congruences. So these are essentially the ways of, so the reason for introducing congruences is that it provides you many important or significant shortcuts when you do computations with congruences. And what we are studying via these properties are these tricks of taking the shortcut using congruences or modular arithmetic. Okay. So here is a simple result. So if you multiply a congruence, if you can multiply a congruence by any integer. Okay. So so suppose you have a congruence like this, then you can multiply both sides of the congruence by the same integer. So if you multiply 321 by 5, you get 1605. Similarly, you can multiply 123 by 5 and you can get 615, and the result is that if you have this congruence 321 congruent to 123 mod 9, then you can multiply both sides of the congruence by the same integer and still have the final result to be congruent mod 9 or mod n. Okay. So, in general, if A is congruent to B mod n, then K A is congruent to K B mod n for any k. Second question, another property is that you may add any integers to both sides of a congruence. So, if A is congruent to B mod n, then A plus k is congruent to B plus k mod n. Okay. So, these are easy to see. For example, if A is congruent to B mod n, then this means that A minus B is divisible by n. So, of course, K A minus K B, which is k times A minus B, will be divisible by n, right? Simple. Similarly, A is congruent to B mod n, this means that A minus B is divisible by n. This implies A plus k minus B plus k, which is actually equal to A minus B, is also divisible by n. So, simple properties like this. So, for example, 328 is congruent to 130 mod 9. So, you can add minus 7 to both sides, and you can get 321 congruent to 123 mod 9, and then you can add minus 7 once more, and you can get 314 congruent to 116 mod 9. Okay? So, you can play these things repeatedly, and sometimes it gives you advantage in calculation. So, arithmetical properties of congruences. So, you may raise both sides of a congruence to the same positive exponent or power. So, if A is congruent to B mod n, then for any positive integer p, A to the power of p is congruent to B to the power of p mod n. And here is a simple situation where you can see why this is true. So, suppose A is, so let us check why this should be true for p equal to 2. So, here is a p equal to 2 case. So, suppose A is congruent to B mod n, then we already saw in the last slide that both sides of the congruence can be multiplied by the same integer, and we will have that the result is still congruent mod n. Okay. So, let us multiply both sides of this congruence by A. So, this would imply that A square is congruent to AB mod n. Similarly, you can again take the same congruence and multiply both sides by B. This would give you BA times B squared is congruent mod n. But AB is equal to BA. So, if A squared is congruent to AB and BA is congruent to B square, that means A square must be congruent to B square mod n. Okay. So, this shows that if A is congruent to B mod n, A square must be congruent to B square mod n. Similarly, you can do it for other powers. Okay. So, for example, you can have the congruence equation 321 is congruent to 6 mod 9, and you can square both sides to get 103041 is congruent to 36 mod 9, or you can cube both sides of the congruence to get another equation. Okay. Any questions? Okay. So, here is another basic property of congruence. Congruences must have the so-called transitive property. So, if A is congruent to B mod n and B is congruent to C mod n, then A must be congruent to C mod n. Okay. So, this is clear. So, for example, A is congruent to B mod n means A minus B is divisible by n. B is congruent to C mod n means B minus C is divisible by n. So, if you add both of these, B and B will cancel and give you A minus C is divisible by n, which is exactly A is congruent to C mod n. So, these are basic ideas of manipulating congruences, and a note of caution is that the modulus must be the same for all the congruences. Okay. So, here is an example, since 103041 is congruent to 36 mod 9 and 36 is congruent to 0 mod 9, it follows that 103041 is congruent to 0 mod 9. But congruent to 0 mod any integer means that integer modulus, the modulus divides the integer, right. So, 103041 being congruent to 0 mod 9 means that 9 divides 103041. Okay. Any questions? Okay. So, here are some more properties. So, two congruences with the same modulus can be added to each other or multiplied to each other. So, suppose you have A minus B A is congruent to B mod n, C is congruent to D mod n, then A plus C is congruent to B plus D mod n, and AC is congruent to BD mod n. And these also you can verify by basic calculations like we did for some of the previous properties. Okay. So, I am not going into the details of the verification. So, here are some examples. So, 3 cubed is congruent to 6 mod n, 5 cubed is congruent to 6 mod 7, and transitivity we can deduce this pair of congruences. So, first of all, 3 cubed plus 5 cubed is 6 plus 6 mod n, which is mod 7, which is 5 mod 7, because 36, because 6 plus 6 is 12 and 12 is 5 mod 7. Similarly, you can multiply these congruences and say that, get that 3 cubed times 5 cubed is congruent to 6 times 6 mod 7, but 6 times 6 is 36. So, 36 is 1 mod 7. Okay. So, the point is that if you have a complicated product like this and you are asked to calculate the remainder when you divide by 7. So, you are asked to simplify it mod 7, then what will you do? Well, what you can do is that you can calculate how much the first factor is mod 7, how much the second factor is mod 7. So, in this case both are 6 mod 7, and then the product will be the product of these remainders mod 7. Okay. So, just to go over the example again. So, suppose we want to find what is the remainder when 3 cubed times 5 cubed is divided by 7. So, we want to, in other words, we want to find out what is the question mark, so that 3 cubed times 5 cubed is question mark mod 7. Okay, and this question mark has to be the remainder. So, it has to be between 0 and 6. So, what we do is that we first notice that 3 cubed is 6 mod 7 and 5 cubed is also 6 mod 7. So, what we say is that, well, we start with 3 cubed times 5 cubed, and you can replace the 3 cubed by 6 and 5 cubed also by 6 because of these congruences mod 7, and but this is 36 mod 7, which is 1 mod 7. Okay. So, the entire big product is just 1 mod 7. The point is that the entire big product might be too large to calculate, but the individual factors might be slightly easier. So, you might be able to calculate the remainders when you divide the individual factors, and modular arithmetic allows you to use your knowledge of the remainders when you divide the individual factors by 7 and combine them so as to get the remainder when you divide the full product by 7. Okay. So, that is the use. Any questions? Okay. Here is another example. So, during a period of 50 days, you put the following amounts of money into your piggy bank. So, day 1 you put 1 cent, day 2 2 cents, day 3 4 cents, day 4 8 cents, etc. So, on the kth day you put 2 to the power of k minus 1 cents. Finally, you exchange the total number of total amount for dollar notes. So, how many cents will be left over? So, of course, 100 cents is $1. So, you have to basically count how many times 100 cents is contained in this total amount of cents. So, it will be some integer number of integer sets of 100 cents, which will give you dollars, and then the remaining will be cents which are left over. Okay. So, essentially the total amount of cents is for 50 days, it is just 1 plus 2 plus up to 2 to the power of 2 to the power of 50 minus 1, so 2 to the power of 49, and you want to find how much is this mod 100. What is the remainder when you divide this by 100? That is the amount of cents that will be left over. So, this is 2 to the 50 minus 1. So, you want to find 2 to the 50 minus 1 mod 100. You want to simplify this. Okay. So 2 to the 50. So, really minus 1 will just contribute minus 1 to the mod 100, right. So, really you need to understand what is 2 to the 50 mod 100. So, 2 to the 50 is 2 to the 10 taken 5 times. So, this is 1024 taken 5 times. Okay. So, this is, so, and 1024 is 24 mod 100, because 1024 is 1000 plus 24, 1000 is divisible by 20 by 100. So, this is just 24 mod 100. So, 2 to the 50, so 2 to the 50 is 2 to the 10 times 2 to the 10 times 2 to the 10 5 times. Okay. So, this is, you are just doing it mod 100. Okay. So, 5 times 2 to the 10, but 2 to the 10 itself is 24 mod 100. So, this is 24 taken 5 times mod 100, right. Okay. So, let us now try to understand what is 24 to the power of 5 mod 100. So, let us do it easily. So, 5 times 24 mod 100. So, again we are just calculating mod 100. So, the point is that 24, if you take a 4 out of the next 24, this is 4 times 6. Now, 4 times 24 is 96, right. So, this is 96 times 6 times 24 times 24 times 24. Now, 96 is very good mod 100 because it is minus 4, right. So, this is minus 4 times 6 times 24 times 24 times 24. But minus 4 and 6 is 24. So, this is minus 24 times 24 times 24 times 24. So, 24 multiplied 5 times is just minus 24 multiplied 4 times mod 100. 24 to the power of 5 is just minus 24 to the power of 4 mod 100. Okay. And you can again write the 4 times 24 out, take a 4 out of this 24, put it on here to get a 96, and do the simplification to get this as 24 cubed mod 100. And you can continue until you get 24 mod 100. So, without doing any real calculation, you have calculated what is 2 to the 50 mod 100, okay, just using the playing with the properties of congruences. So, ultimately you want 2 to the 50 minus 1 mod 100. So, 2 to the 50 is 24. So, this is 24 minus 1 mod 100, which is 23. Okay. So, it needs a bit of getting used to. So, it is as if you are doing usual arithmetic, but whenever convenient you can replace a number by something different which is mod, which is congruent to the same number mod 100. Okay. So, you can, it is exactly like doing usual arithmetic, but at any stage you can replace an A by a B as long as A is congruent to B mod 100. Okay. So, that is kind of the how to swim with it. Okay. Any questions? Okay. So, here is an application to congruence mod 9. So, is 1, 2, 3, 4, 6 divisible by 9. So, let us do it. So, 1, 2, 3, 4, 6 is just you write down the decimal expansion. So, if it is a decimal expansion, then this is the natural interpretation of what you mean by 1, 2, 3, 4, 6, right. So, 6 comes with a power of 10 to the power of 0, so 1. 4 comes with 10, 3 comes with 10 square, and so on. Okay. Now, here is the magic of congruences. So, you want to understand whether this is divisible by 9. So, in other words, is 1, 2, 3, 4, 6 congruent to 0 mod 9? This is the question, right? So, basically you want to calculate what is 1, 2, 3, 4, 6 congruent to mod 9. Okay? You want to simplify 1, 2, 3, 4, 6 mod 9. So, how do you do it? You write it in these terms of this expansion, and notice that any power of 10 for any k, 10 to the any power of 10 is 1 mod 9. Okay? Because the immediately previous number will be 99999, you know, a number of times. So, for example, the previous number to 100 is 99, previous number to 1000 is 999, all of these are divisible by 3 or by 9. So, 10 to the k is 1 mod 9. And there is also a more formal way to see this. Notice that 10 is 1 mod 9 clearly, because 10 minus 1 is divisible by 9. So, 10 is 1 mod 9. So, 10 squared is congruent to 1 square mod 9, because you can take powers, but this is exactly 1 mod 9. Similarly, any power of k, any power of 10, any kth power of 10, 10 to the k is congruent to 1 to the k mod 9, and 1 to the k is just 1, right. So, 10 to the k is 1 mod 9. So, that is what we are going to use. So, we are studying this mod 9. So, again any appearance of A we can replace by B if it is if A is congruent to B mod 9. So, all these powers of 10 are congruent to 1 mod 9. So, modulo 9 we can replace all of them by 1. Okay. So, this is 1 plus 2 plus 3 plus 4 plus 6, which is 7 mod 9. So, the remainder, so the answer is not 0 mod 9. So, 1, 2, 3, 4, 6 is not divisible by 9. Any questions? Okay. So, let us now formalize the previous example into a criterion for divisibility by 9. So, let S be the sum of the digits in the decimal representation by a positive integer n. Then n is congruent to S mod 9, and n is divisible by 9 if and only if S is divisible by 9. So, let us go back to the previous example and see what this is. Notice that the ultimate answer was the sum of the digits of this number in decimal representation. And the theorem is essentially formalizing this and is telling you that this is always going to be true, that any number is always going to be congruent to its to the sum of its digits in decimal representation mod 9. So, and therefore, a number is divisible by 9 if and only if the sum of its digits is 0 mod 9, that is the sum of its digits in decimal representation is divisible by 9. Okay. So, let us take the example, let us see why that is true, and actually the argument is pretty much the same as what we did for the example. So, you write the number n in terms of its decimal expansion, and notice that modulo 9, each of these powers of 10 is 1. So, modulo 9 you can replace each of them by 1, and this is congruent to ak plus ak minus 1 plus da 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 plus a1 plus a0 mod 9. Okay. So, that is all that there is to it, and this is exactly the sum of the digits of n in its decimal expansion. Any questions? Okay. So, here are some simple examples. So, previously we studied whether 1, 2, 3, 4, 6 was divisible by n, and the answer was no. Now, the question is 1, 2, 3, 4, 5, 6 divisible by n. So, we have added a 5, and what about 1, 2, 3, 4, 5, 6, 7, 8? So, well, now we have an easy criterion. So, you just form the sum of the digits in the decimal representation. For 1, 2, 3, 4, 5, 6, the sum of the digits is 21, so it's not divisible by 9 because 21 is not divisible by 9. On the other hand, for 1, 2, 3, 4, 5, 6, 7, 8, the sum of the digits is 36. 36 is divisible by 9, so the original number 1, 2, 3, 4, 5, 6, 7, 8 is also divisible by 9. Okay? So these are some applications of this criterion. Okay, so we will continue with more applications of congruences, but for now we will take a 10-minute break. Okay, so let us continue with the lecture. So before the lecture, before the break, we were studying about the various properties of congruences. So one of the uses of congruences which we studied was checking divisibility by 9. So another one is checking product. So suppose you are given a product A times B is equal to C. So you should imagine a product of very large numbers like this, and you want to check whether the multiplication is correct or not. So one check which you can do is that you can see whether this equation is true modulo n. In other words, modulo 9. In particular, in fact, you can check whether this equation is true as a congruence equation modulo any n. So if this is true, if this equation is true, if the multiplication is correct, this would in particular imply that A times B is congruent to C mod n for any n, So in particular n equal to 9. Okay. But once you try to check this for n equal to 9 instead of n, instead of a general n, what you can do is that you can now replace, you now observe or recall that A is congruent to S mod n, where S is the sum of the digits of A in the decimal representation. Similarly, B is congruent to T mod n, mod 9, where T is the sum of the digits of B in the decimal representation, and similarly C is congruent to U mod n, mod 9, where U is the sum of the digits of C in decimal representation. So then, using the properties of modular arithmetic, you can replace this modular equation by this congruence equation by the equation S times T is congruent to U mod n. Okay, but by replacing A by S, B by T, and C by U. Okay. So the logic is that if A times B was indeed equal to C, if the multiplication was indeed correct, then in particular it should be true that S times T is congruent to U mod 9. And the advantage is that these A and B and C might be huge numbers which are difficult to and the multiplication may be difficult to check directly, but S and T and U might be small numbers because these are the sum of the digits of A, B and C respectively. So these might be small numbers. So this congruence equation mod 9 may be easy to check. So this is the logic. So for example, without evaluating the product, show that the following multiplication cannot be correct. What you do is that you say that, well, if this multiplication was indeed correct, then this congruence equation must be true, this congruence equation must hold, but you calculate the sum of the digits and check that mod 9 this is not going to work because 8 times 2, the left hand side mod 9 is 7, whereas the right hand side is 6 mod 9. So you conclude that the multiplication is incorrect. However, this is not an if and only, this is not a guarantee. So it might be the case that even if the congruence equation S times T is congruent to U mod 9, even if this is correct, it might be so that the original equation is incorrect, but the point is that it gives a one-way check. So if you check, if you verify that this congruence equation doesn't hold, then in particular the original equation cannot be held and the multiplication cannot be true. The multiplication is not correct. Okay. Any questions? Okay. So now we are, with all this background in congruence, in manipulating congruences, we are ready to step into coding theory proper. So to understand coding theory, we have to understand information transmission, because coding essentially comes from the theory of transmission of information. So what is information transmission? For information transmission, you need an information source, which are messages or information to be sent, and encoding of the information source. So words and images are converted into numbers, for example. An information channel, so the signal is sent, so this is encoded into a signal, and the signal is sent through a channel that is a machine, for example, computer or internet or cables and so on. A noise or an error source, which is a distortion added to the signal in a channel. So, for example, this is caused by nature, like lightning, or caused by a man. So, for example, when I am typing my information into the computer, it can be I can make a human error, or by defective parts in a machine and so on. So, these are unavoidable errors which come in the transmission of information. So, then this transmitted information arrives to the user, but this is the signal that he has received. So, remember that we in the first step we had encoded the information into a signal or a code. So, we have to now decode it back to information that is intelligible to us. So, maybe we had encoded an image in the form of some numbers. So, we want to now decode the image back, decode the number back into the image that we want to see. Okay. So, and the problem is that this signal is sometimes distorted or partially lost during transmission because of these noises and human errors. And the sink for the information is the final outcome. So, in this entire process can be summarized in the form of a flow chart. So, this is the information source. This gives you, here you do an encode, this information source, the original information you encode into a signal. This signal you transmit via information channel where it picks up noise, where it is sort of smeared with noise, and then you receive this noised version of the signal at the side of the user, where you do decoding, and then this gives you the final outcome of the transmitted information. And it is, and coding theory comes up in the part of encoding, so that at the stage of encoding you have to do it in a proper way, so that you can sort of send the information in the most economical manner on one hand, and on the other hand you want to have good decoding properties. So, you should be able to decode easily and accurately, and if possible you should also be somewhat tolerant to errors. So, if the noise is small, if the human error is small only at a few places in the transmitted signal, then you should be your encoding and decoding procedure should be robust to that. Okay. So, let us see what we have. So, here so for electron, so one popular representation is binary representation. So, for electronic devices, most electronic devices can be in one of two states, so on or off, and it is convenient to represent the two states by 0 or 1. And if you want to represent 4 states, the combination of ons and offs, so you can do it using 2 bits, so 0, 0, 0, 1, 1, 0 and 1, 1. And in general, you can represent 2 to the k states in the form of k bits. Okay. Here is another example. This is the decimal system. So, historically and physically, counting is usually done in groups of tens, and the basic reason is as follows. So, you see these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. These are basically these are concepts, right? And why do we count in groups of 10? So, one natural explanation is the following. So, what is the most naive rudimentary way of counting? So, suppose you want to count, you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that is all that you can count by hand. So, in the most easy, elementary, basic way of counting, probably the one of the first methods which occurred to human beings, you can count together, you can keep track of only 10 numbers. So, that is why you count in batches of 10, and once you have, if you need to count more than 10 objects, what you do is that you count 10 like this, and then remember that you have done it once, and then start a new batch. Okay. So, that is why it is natural to count in terms of 10, and using the base of 10, you can encode the numbers in 10 basic symbols or digits, 0, 1, 2, 3, 4 up to 9, and just as we saw a few slides before, you can represent any number in base of 10 as an expansion like this. Okay. Any questions? So here is some more on the binary system. So counting can also be done in groups of 2's. So this is more suited, this is suited less to the way human beings count and more suited to the way machines operate or electronic devices operate. So 0 can be thought of as 0, 0, 0, 1 can be thought of as 0, 0, 0, 1, 2 can be thought of as 0, 1, 0, 3 can be thought of as 0, 1, 1, and essentially these are expansions. So just like for decimals, for the decimal expansion or the base 10 representation of a number, you have expansion like this. Similarly, these binary representations are also given by this sort of expansions. So these equations that we have here are examples of this sort of expansion. So the change of base from decimal to binary means that instead of powers of 10, we are doing this in terms of powers of 2. And in decimal expansion, the symbols, the RKs could be anything between 0 and 9. In binary, RKs can only be between either 0 or 1. Okay? Only be between 0 and 1. Any questions? So the binary representation of a positive integer n is just RK, RK minus 1, da da da, R2, R1. The subscript 2 here is to emphasize that the so-called base of the representation is 2. And it may be omitted if there is no ambiguity, and if there is any doubt, we should write it in. Each of the digits in the binary representation is called a bit, and this is kind of more suited to how computers operate, for example. So here is an example of binary representation. So convert 235 into a binary representation. So this is a sequence of divisions. Essentially, you can think of it as Euclid's algorithm. So basically, what you do is that you divide, you keep on dividing the number by 2. So you divide 235 by 2. This is the quotient, and this is the remainder. So this is division. And then from every step, you take the quotient and divide it again, and you keep track of the remainders, and then you just list the remainders in the decreasing order like this. Okay? So that gives you the binary representation. And if you are curious, you can check that because of this division procedure, when you expand this in terms of a series like this, the first one, this one will have 2 to the power of k, and so on. Okay? So this is some, this is a natural description of how to obtain, or an algorithm of how to obtain the decimal representation or the binary representation of a number which is given to you in decimals. Okay? So any questions? So the binary, the concept of binary, just like the concept of decimal representations is also very, very old and natural. Similarly, the concept of binary representation is also old and natural. So one of the earliest examples of binary symbols is the ancient Chinese Bagua symbols used in divination. So it consists of juxtapositions of short and long line segments. So the short, so you can see the short and long line segments here, for example, or here in these patterns. So the symbol double dashed means 2 small dashes means female, 0, and the symbol 1 long dash represents male, which is also represented by 1. So you can, these groups you can represent in decimal like this. Okay, so this is some historical context. So let's now get back to our discussion of coding theory, and what we already discussed a bit or referred to a bit was that errors can occur in transmitted codes. So for example, you might send 11111, but the central one can be switched by some noise or some mechanical error to a 0. Okay. So, the question is, if errors occur in only at a few bits, how can we detect them? So, the point is that in industry we are always striving to design better and better machines which make fewer and fewer errors. So, we can assume that the errors are very few, but still there will be errors. So, how can we make use of the fact, take advantage of the fact that the errors are very few and devise methods to correct those errors, even if they are present when the information is transmitted to us. So, some common errors in writing a number sequence are of the following forms. So, one common error while writing a number sequence is interchanging two adjacent digits. So, maybe I am typing very fast and 78 I type as 87. Okay. So, that is one possible mistake. Another mistake is that when I was supposed to write 7, I punch in 9. That is another, so that is a single error. So, transposition error is when you just interchange two adjacent digits, and single error is just by mistake you flip one digit to something different. Okay. So, so these are called error detecting codes. So, basically the idea of these codes is to understand is to design codes where you can detect this sort of simple errors, okay, which are few in number. So, for instance, if you look at car registration numbers or identity card numbers, you must have noticed that there is often a letter at the end of the number, right. The question is why there is a letter at the end of a number. You can, you could just give me the number. I mean, why is there a letter tagged along at the end? So, what is the meaning of this letter? What is the significance of this letter? So, these letters, so the point of these letters is precisely to do these error checks and if possible error correction. So, the point is that these letters can detect simple errors in writing the numbers and can prevent forgery. So, here is a simple analogy. So, suppose I say Monday 01/10/2001. Okay. So, 1st October 2001 Monday. Now, the point is that when I say 1st October 2001, I am already giving you all the information, right, because you can go back to a calendar and check what the date is. So, why do I need to also say Monday? The reason for also saying Monday is that this date is a long sequence of numbers. So, I might make an incidental error while typing it in. So, maybe I make a transposition error. So, I interchange two adjacent digits, or maybe I make a single error. So, I change one of the digits into what it was not originally. So, the point is that if I make any of these simple errors, then with a very large probability, with a very large chance, there is a high chance that the changed date will not be a Monday. So, by tagging along Monday, by tagging along the word Monday along with the numerical date which already contains in principle all the information, by tagging the information of Monday along with it, I am creating a check. So that someone can check that, I need to, suppose I need to submit this date somewhere. So, I say Monday 1st October 2001, and then the person who receives it immediately checks whether the claimed numerical date was indeed a Monday, and if it is not a Monday, that is an immediate alert that the numerical date I submitted was wrong. Okay? So, that is kind of the way it works. So, this is a very simple example of encoding. So, there is a certain date which I want to refer to. So, this date I encode as a number tagged along with a word. So, in some sense, I am this particular date which I want to refer to, I am expressing it in terms of a code word, which is first a word, the name of the day of the week, followed by a numerical date. Okay? So, this is my code word for that particular day I want to refer to. So in other words, this is a very simple example of an encoding strategy which gives you a simple way to check for easy, basic errors. Okay. So we will study more complicated encoding strategies. So this will be the subject of encoding, which we will go on to next. But for today, the time is up. So I will stop here, and we will continue from encoding in the next lecture.